of a test can be defined in two different ways based on the graph. The graph may be directed graph or it may be undirected graph. First, we'll have discussion about undirected graph. Okay. Let g of v comma e be an undirected graph for v belongs to capital V. Degree of v is equals to number of edges incident from that vertex. Number of edges incident from that vertex. Okay. This is a definition of degree of a test in undirected graph. Let me take simple example to get clear idea. Right. So in this graph, just observe in this graph, we have self loop, right? We have self loop and we have parallel edges also. Now we are talking about the degree of each and every vertex. So most important point, just observe degree of A. Observe how we count degree of A. How many edges incident from A? So clearly it is a one edge which is incident from A, right? It is a second edge incident from A. It is a third edge incident from A, okay? And it is also fourth edge incident from A. It means that whenever we have a loop, then we can count degree of that vertex is 2, okay? Means with respect to that loop, degree is 2. Clearly, A is having self loop, right? When A is having self loop, so degree of A with respect to this loop is 2. Every self loop is providing degree is 2 for that vertex, okay? So therefore, degree of A is equal to 1, 2, 3, and then 4. Degree of A is equals to 4. Similarly, degree of B is equals to degree of B equal to, so 1, this is the edge incident from B, this edge incident from B, it is also incident from B. Total 3 edges are there. 3 edges. And whatever degree of D, degree of C first. Degree of C 2. And degree of D is equals to 3 like this. Okay. So it is a definition about degree of vertex. What you have to remember in this? If a vertex is having self loop, that self loop will produce 2 degree for that vertex. 2 degree for that vertex. Is it clear? Right. Okay. Now if I take sum of degrees of all these vertices, for example, okay, that is degree of A plus degree of B plus degree of C plus degree of D, which is equal to, by summing up all these values, 4 plus 3, 7 plus 2, 9 plus 3, 12, that equal to 12, which is always equals to 2 times of number of edges. 2 times of number of edges. See how many edges we had. So let me give names for these edges. We can say E1, it is E2, E3, E4, E5, E6. Okay. So there are total 6 edges are there. Therefore, 2 into 6 is equal to 12. It is known as some degrees of vertices theorem. Okay, some degrees of vertices theorem. Okay, what is some degrees of vertices theorem? Let me write that point. Sum of degrees. Sum of degrees of vertices theorem. is also known as handshake lemma. Handshake lemma. So it says that sum of degrees of all vertices must be equal to summation I runs from 1 to n. Degree of all vertices must be equals to 2 times of number of edges. 2 times of number of edges. Okay. 2 times of number of edges. There's some degrees of vertices theorem. Clear? So why it is 2 times of number of edges? The proof is very simple. Just observe. Suppose if I have edge between two vertices, let it be vertex A and vertex B, like this, vertex and vertex B. Okay. So here, if I have two vertices, vertex and vertex B, clearly this edge is producing 2 degree, 1 degree with respect to A and 1 degree with respect to B. Okay. So what is the degree of A here? Degree of A is equals to 1. What is the degree of B? Degree of B is equals to 1. If a vertex having degree 1, that vertex is called pendant vertex. Pendant vertex. Okay. So A is pendant vertex, B is also pendant vertex. Clear? So clearly this edge, let me name it as E1. E1. E1 is contributing how many degrees? 2 degrees. One for A and one for B. Okay. E1 is contributing 2 degrees. One for A and one for B. Suppose assume that there is a vertex A. There is a vertex A. This vertex A is having self loop. Just assume that the vertex A is having self loop. Self loop. Now I'm calling that edge is something like E2. E2. Tell me what is the degree of A now? Obviously, degree of A is equals to 2 only, right? So as I already mentioned, whenever vertex is having self loop, then with respect to that self loop, it is producing 2 degree for that vertex. Clearly, one edge is incident from that vertex and one edge is incident to that vertex. Therefore, degree of A is equals to 2. Clear? What did you notice from these two examples? So I have one edge G1 which is contributing degree 2, 1 degree for A, 1 degree for B. And I have another edge G2 which is self loop and it is also contributing degree 2. It means that whenever we see any edge, please observe, whenever we see any edge, that edge is contributing 2 degree, 2 degree, 1 degree for one end vertex and 1 degree for other end vertex. Suppose if that edge is associated with self loop, then that edge is contributing 2 degree for that vertex. Okay. So each edge is contributing 2 degree. Each edge is contributing 2 degree. But how many edges are there? Clearly in the graph G of E comma E, how many edges are there? Let me write that point. Let G of V comma E be an undirected graph. Be an undirected graph. Be an undirected graph. Okay. If G of E comma be an undirected graph, then summation I rise from 1 to n degree of E equal to 2 times of edges. Now see here in this graph, how many number of edges are there? Total number of edges. How many number of edges? E number of edges. So each edge is contributing 2 degree. Therefore, sum of degrees of all vertices equal to 2 times of edges. Okay. So let me write that point. The proof is very simple. Each edge produce 2 degrees. 2 degree. 2 degree. So why we are calling it 2 degree? Just observe this one here. E1 is producing degree 1 for A, degree 1 for B. Therefore, it is 2 degree. And E2 also producing 2 degree. Therefore, each edge produce 2 degree. And the total number of edges are are E. Total number of edges are E. Therefore, sum of degrees Sum of degrees of all vertices is equals to 2 times of number of edges. If each vertex is contributing 2 degrees, then the sum of degrees of all vertices must be 2 times of number of edges. Okay. So hence the theorem is proved. Summation I runs from 1 to n, degree of vi must be equals to 2 times of number of edges. 2 times of number of edges. Okay. This lemma is called handshaking lemma. Okay. So I hope it is very clear. This handshaking lemma. This is called sum degrees of vertices theorem. Sum degrees of vertices theorem. Right? This theorem, whatever we covered now, that is only for undirected graph. Suppose if the graph is directed graph, if graph is directed graph, let me discuss the directed graph also, so that we will get more clarity. Suppose let g of v comma e be a directed graph. Let g of v comma e be a directed graph. Okay, we are considering this time graph is directed graph. Whenever graph is directed graph, then we can discuss degree of vertex with respect to two parameters. One is in degree, another one is out degree. Okay, so what is the meaning of in degree and what is the meaning of out degree? Just look at this example. Suppose I have four vertices A, B, C, D, four vertices, and from A to B we have edge direction, and A to C we have edge direction, and D to A we have one edge direction. Okay. Just assume that this is a given graph. Okay. Now, if I want to find degree of A, then the degree of A can be computed by using in degree as well as out degree. First, I want to discuss in degree of vertex A. In degree of vertex A is defined by degree plus of A. Plus means in degree, minus means out degree. Okay. In degree of A. How many number of edges incident to that vertex? How many number of vertices? Sorry, how many number of edges incident to that vertex is called in degree of that vertex. Look at how many of them, how many edges incident to that vertex. For example, if I consider A, how many edges incident to that vertex? So clearly only one edge, only one edge. This is only one edge, only one edge. What is that edge? Suppose if I call this edge is E1, E2, E3, E4, E5, and then E6. Clearly, only one edge incident to A. Therefore, in degree of A is equals to 1. 1. Who is that edge? Obviously, that edge is equal to E3. E3. Similarly, in degree of B, in degree of B, number of edges incident to B, incident to B. How many? E1 incident to B, E2 also incident to B. Therefore, 2. What are they? E1 comma E2. E1 comma E2. Next, in degree of C, in degree of C. That is equal to in degree of C means here it is E4, E4. Of course, E6 also there, E4 and E6. E4 and E6. Therefore, 2. That is E4 comma E6. Please understand E4 comma E6. Then what is the in degree of D? In degree of D. So in degree of D means E5, E5, only E5 is available. That is only one. That equals to E5. Clear? E5. Next, what is the meaning of out degree? Out degree is nothing but number of edges incident from that vertex. In degree means incident to that vertex. Out degree means incident from that vertex. So out degree can be defined as degree minus of A. This is a notation for defining out degree. So degree of out degree of A. Out degree of A. How many edges incident from that vertex? That is two edges. So that equal to, who are they? E1 comma E4. E1 comma E4, right? And similarly, out degree of B. We want to compute out degree of B. And also we'll compute out degree of C. We'll compute out degree of D. Okay. Can you try now what is out degree of B? What is out degree of B? Yes, I hope you tried. Let me explain. How many number of edges incident from the vertex? Of course, no edge is incident from the vertex. Therefore, out degree of B equal to 0. 0. Out degree of C. How many edges incident from C? Only one edge. Only one edge. That is E5. Who is that? E5. I'm writing edge also in the bracket. Please understand. I'm writing edge also in the bracket. Okay. Degree of out degree of D. Out degree of D means obviously three edges. Okay. Who are they? E2, E3, E6. That's it. Okay. So it is nothing but in degree and it is nothing but out degree. Is it clear? Suppose if I sum up all these in degrees of all vertices, if I sum up all these in degree vertices, just understand this point clearly. And if I sum up all these out degrees also, okay, which is equals to this total value is equals to summation I runs from 1 to n, 1 to n. Or else we are going to add only four vertices, right? Let me write only those four vertices. If I sum up all these values, this is equals to 6. This is equal to 6. And similarly, if I sum up all these values, we'll get result equal to 6. What did you notice from this? Sum of in degree of all vertices must be equal to sum of out degree of all vertices. And that value is equals to total number of edges. Total number of edges. How many edges we had here? 1, 2, 3, 4, 5, 6 edges. Therefore, it is total number of edges. Okay. So from this, we can conclude that summation I runs from 1 to n in degree of all vertices is equals to summation I runs from 1 to n out degree of all vertices is equals to total number of edges. Right? Total number of edges. Clear? So this is the meaning of degree of a vertex in directed graph. Is it clear? So what we covered so far, we started with graph definition. After completion of graph definition, we have seen what is the meaning of null graph, what is the meaning of trivial graph, right? So afterwards I explained how to compute degree of a vertex. Then we started simple graph. Simple graph. There are three important properties of simple graph. Every simple graph, every simple connected graph must contain at least n minus 1 edges, at most n into n minus 1 by 2 edges. And number of simple graphs are possible with n vertices means 2 to the power of n into n minus 1 by 2. And number of simple graphs are possible with n vertices and m edges means n into n minus 1 by 2 c m edges. Okay. And also we have seen some degrees of vertex theorem, that is sum of degrees of all vertices must be equals to 2 times of number of edges. So in the next video, I'm going to discuss so many worked examples based on some degrees of vertices theorem. You no need to worry about practice problems. Okay. So I will cover almost 20 problems based on only some degrees of vertices theorem. That's why don't worry about practice problems. First, learn theory part. Okay. So afterwards, I'll introduce uh, all practice problems. Okay. First, we'll discuss practice problems. Afterwards, we'll discuss gate problem based on some degrees of vertices theorem. Right. So some degrees of vertices theorem completed. Now, by using some degrees of vertices theorem, we can derive some important statements. Okay. Look at what are the statements now. Note The first one, let me read all the points like once again. First one, sum of degrees of all vertices, summation I runs from 1 to n, degree of all vertices must be equal to 2 times of number of edges. It is called sum degrees of vertex theorem, which is handshaking lemma. Okay. So what is the meaning of the statement? Sum of degrees of all vertices equal to 2 times of E means anything multiplied by 2 will always gives even number. Will always gives even number. Therefore, the statement meaning is sum of degrees of all vertices. Sum of degrees of all vertices must be an even number. Must be an even number. How can I say even number? Because sum of degrees of all vertices must be equal to 2 times of edges, right? 2 times of edges means it must be even number. Okay, it must be even number. Next, third point. Suppose if a vertex is having degrees odd, that vertex is called odd vertex. If the vertex is having degrees even, that vertex is called even vertex. Even vertex. Okay. So for example, if I take simple example like I have 4 vertices. Okay. Here, if you see what are the odd vertices and what are the even vertices. The degree of vertex is odd, that is called odd vertex, right? So clearly degree of A is equal to 3 because there are 3 edges incident from A. Therefore, degree of A equal to 3. 3 means odd, therefore A is odd vertex. Similarly, degree of D also 3. Therefore, it is also odd vertex, right? What about even vertex? Degree of B equal to 2, which is even, therefore B is even. Small correction is required here. D degree is 3, therefore D also odd degree vertex, right? And B and C having degree 2 only, therefore B is even vertex and C also even vertex. Is it clear or not? Okay. In a graph, if any vertex having odd degree, that is called odd vertex, and if the graph in any vertex having even degree, that is called even vertex. Okay. Now, what is the importance of this statement here? What is the importance of the statement? So just now we have seen, suppose if I have n into n minus 1 by 2 edges, just assume that I have n into n minus 1 by 2 edges, like E1, or I can say suppose E1, E2, E3, E4, E5. Suppose I'm taking only 5 edges. 5 edges. Assume that there is a graph. In that graph, we have only 5 edges. Okay? 5 edges. Now I want to find degree of E1, and also I will find degree of E2. Okay? Degree of E2. Next, degree of E3. Next, degree of E4. Next, degree of E5. Okay. If I sum up all these values, degree of E1 plus degree of E2 plus degree of E3 plus degree of E4 plus degree of E5, if I sum up all these values, what will you get according to handshaking lemma? It must be 2 into total number of edges. 2 into total number of edges. But 2 into total number of edges means it must be even number. Therefore, let me write it is even number. It must be even number. Correct? Even number. Now I'm introducing most important point here. Please listen. Suppose assume that degree of E1 is even. Degree of E1 is even. Even means the degree of E1 is even number. Okay. Similarly, degree of E2 also even. Even. Assume the degree of E3 also even. Degree of E4 also even. degree of E phi also even. If I take all our even numbers, sum of all even numbers again even number. So obviously it is correct. Sum of all even numbers always even number. It is correct. Okay. Second case, again that is case number one. Case number one. Now I'm taking second case. Second case. Suppose the first one is even, second one is also even. Okay. Third one is also even, but fourth one is odd degree, and fifth one is odd degree. Odd degree. Now, if I sum up all these values, see, even plus even plus even, this part is giving even number. Even number. So if I take odd plus odd, for example, 3 plus 3, that equal to 6, which is even number. Odd plus odd, right? That is even number. Okay, it is also even number. Okay. Now, even number plus even number, obviously it is providing even number. Even number. So second case also okay. First case okay, second case also okay. So why we are discussing all these case studies? Let me explain this case studies first. Afterwards, I'll give a conclusion. Okay. On third case, it is interesting. Third case, suppose assume that degree of E1 is even, degree of E2 also even, but degree of E3 is odd. Degree of E4 is also odd. Degree of E5 also odd. Okay. E1 is even, E2 even, E3, E4, E5 they are having odd. In that case, if I sum up these two, I'll get result is even. Even plus even means even. But if I sum up all these three, addition of three odd numbers is not even number. Please observe. For example, if you take 3 plus 5 plus 7, 3 plus 5 plus 7, which is equals to 15. 15 is not even number, right? Definitely you'll get it is odd number. Odd number. Okay. This total part must be odd number. Now between these two we have addition symbol, right? Now if I add these two, even plus odd means again it is odd number. But what does your theorem says that? The theorem says that sum of degrees of all vertices must be even number. Now we got contradiction. Left side we have odd number, right side we have even number, which is not possible. Which is not possible. Which is not possible. Do you know what is the importance of studying these case studies? Please look at once. First one. Suppose if every vertex is having even degree, look at this one. If every vertex is having even degree, then there are no issues. Sum of degrees of all vertices is even. Right? Suppose if I have even degree vertices are 3 and odd degree vertices are 2. It means in this case also we are getting result is even. There is no issue. There is no issue. In second case, remember how many number of odd vertices are there? Please look at here. How many number of odd vertices are there? 2. There are 2 odd vertices are there. 2 means even number of vertices. Even number of odd vertices. Therefore, the total result is even. No problem. But if you observe third case, how many number of odd vertices? Please count 1, 2, 3. There are 3 odd vertices. 3 odd vertices means odd number of odd vertices. Whenever we have odd number of odd vertices, definitely it is not matching with the sum of degrees of vertices theorem. What does it mean? It means that in any simple graph, the odd degree vertices must be even. Odd degree vertices must be even. So please look at this third case. Odd degree vertices are how many? 3. 3 odd degree vertices. 3 odd degree vertices. 3 is not even. Therefore, it is not a simple graph. It is not a simple graph. Please understand that point. Okay. So what I'm going to conclude from this, the most important note is that is third point. Most important note, that is third point. In a simple graph, the total number of odd vertices must be even. Total number of odd vertices must be even. Okay. Yeah. What does it mean? Total number of odd vertices must be even. Suppose if you have 3 vertices of odd, it is not valid. If you have 4 vertices of odd, it is valid because 4 is even. Okay. The total number of odd vertices must be even. The total number of odd vertices must be even. What does it mean? I can have odd vertices like this. Odd vertices. Number of odd vertices. I can accept 2, which is even. I can accept 4. I can accept 6. And so on, anything I can accept with the form of 2n format. Okay. Total number of odd vertices in a graph must be even. Okay. So in a simple graph, the total number of odd vertices must be even. Okay. This is the most important point you have to remember.